Okay, so we want to look at trig substitution, evaluating integrals with trig substitution. Now, first of all, there's a couple I want to be sure we all remember. When we talked about trigonometric integrals, we talked about the Pythagorean identities. So that's going to be important here as well. But I want to just, I want you to think about something. If you have, let's suppose that you have a situation like this. X equals tangent, well, let me do this. Let me say some number, A tangent theta. Let's suppose that you have that. X is equal to A tangent theta. Well, think about a triangle where we have theta. Now, of course, this means that if I divide by A, I have tangent theta equals X over A. Now remember, tangent is the opposite over adjacent. So there's what we have. And I still don't have the third side, but remember, Pythagorean theorem says that that third side squared is equal to the sum of the squares of the other two sides. So what we have here, the length of this side is just going to be A squared plus X squared. So that's pretty clear, right? Now, let's go this way. Well, let's say that, let's suppose that X equals A secant theta, like that. Then that means that secant theta is equal to X over A. Now, remember, so let's just draw the same triangle, or one that's a lot like it. Now, remember, secant is hypotenuse over adjacent. Now, if that's hypotenuse over the adjacent, remember, using Pythagorean theorem, we can get that this side right here is X squared minus A squared. Okay, everybody see that? Just using Pythagorean theorem. Now, one more that we'll look at, and that is, let's suppose that X is equal to A sine theta. Well, then that means that sine theta is equal to X over A, and we make the same triangle. Here's theta. And now we have opposite over hypotenuse, and this right here would be A squared minus X squared. Okay, so if you remember these three, so in other words, look at this. We've got the hypotenuse, the opposite side, and the adjacent side. And they correspond to three different square roots, right? On the one hand, you've got A squared plus X squared. Then you've got X squared minus A squared. And then you've got A squared, well, here's X squared minus A squared here. Let me see here. A squared minus X squared, and here, X squared minus A squared, here's A squared minus X squared. Why is sign different? Well, in using Pythagorean theorem, I have this side squared, okay? So whatever we'll call this C squared plus X squared. Okay, you got it? Okay, and then we just solved, okay? Any other questions? Now, what we want to do is we want to keep these three things in mind, and also we want to keep in mind the Pythagorean identities. The Pythagorean identities says this, that if you have tangent squared x plus 1, that equals secant squared x. Okay, so we want to keep that in mind. We also want to keep in mind that that means that secant squared x minus 1 equals tangent squared x. So, in other words, really this Pythagorean identity right here. And we want to think about both forms. Tangent squared x plus 1 equals secant squared x, and secant squared x minus 1 equals tangent squared x. And the other thing we want to do is we want to keep in mind that 1 minus sine squared x is equal to cosine squared x. Another Pythagorean identity. Okay. So this is the basic knowledge that we need in going into this trig substitution. So let's look at just a problem that we would use this information to solve, or an integral that we would use this information on. Let's suppose that we have this. Let's suppose that we have 4 over x squared 16 minus x squared. Of course, dx here. Now, when we're going to employ this trig substitution that I'm going to show you, we're looking for things like is on those 3 triangles. In other words, we're looking for the square root of a constant squared plus x squared. We're looking for the square root of x squared minus a constant squared. And we're looking for the square root of a constant squared minus x squared. So we're looking for those things, and we'll make the appropriate substitution. So now this one right here, we've got a constant squared minus x squared. Well, that corresponds in our triangles to letting x be a sine theta. Well, here's what we do. Notice I've got a 16 right here. I'm going to say, okay, what is the square root of that? It's 4. So I say 4 sine theta. That's the substitution we'll make. It's just the square root. So 16 is a squared. So that means a is 4. Now, once we do that, we immediately say, okay, then dx is 4 cosine theta d theta. That's what we do immediately. Okay. And then we substitute in. So here's what we have now. Up top, in place of dx, we have 4 cosine theta d theta. So now look, we got 4. And then we've also got another 4, right? Right? Cosine theta d theta. So what I did was I put this whole thing in place of dx. And there was already a 4 up there. Yes, ma'am. Yeah. I just differentiated this, just like usual when we let u be something. Okay? Okay, so there's what I get up top. Now, on the bottom, we get 16 sine squared, right? See? So what I did was I just put in place of x squared, or in place of x, I put 4 sine theta, which is going to be 16 sine squared theta. Okay? Any questions about that? Okay. Then I've got this. I've got 16 minus 16 sine squared theta. And it looks like at that point I've substituted in everything, right? This thing is now no longer in terms of x, it's in terms of theta. So let's just take a minute and just go back over what we have here. This right here, this came from this, the derivative, right? And then we have our x right here. That is this right here, which is that. And this dx is also in yellow. Okay? And then this part right here is, of course, this. Okay? Any questions where I got all of this? Now, so here you're thinking, well, congratulations. You've taken a rather tame-looking integral and made it into a mess. Thank you. Thank you for that. Well, hang on, because notice that this mess, what we're doing here is we're using the trig functions and their properties to simplify the integral a little bit. So look at this. The 4's times 4 cancels with that 16 on the bottom. And now, here's what I want to do. I want to see if I can maybe simplify this a little bit. Here's what we have. Up top, we still have the cosine theta d theta. But on the bottom, now we've got sine squared theta. And I want to do this. I want to factor out the 16. Okay? Does everybody dig what I did there? Now, the square root of 16, of course, is 4, so let me pull a 1/4 out front. And now I've got this. I've got cosine theta d theta over sine squared theta. And then here's what we have, 1 minus sine squared theta. Now, remember that 1 minus sine squared theta is cosine squared theta. So let's go ahead and do that. We've got cosine theta d theta. Here is sine squared theta. And this is cosine squared theta. Okay, that's pretty cool. Now look, I'm going to take the square root of cosine squared theta and I'm going to call it cosine. Now, I normally can't do that. I normally would have to say the square root of cosine squared theta is the absolute value of cosine. But here's what I'm assuming. I'm going to assume, remember, I'm just using these trig functions and their properties to take an integral that's a little bit too complicated for me and simplify it. So I'm restricting the domain of theta. I'm restricting theta so that, yeah, cosine theta is positive. Okay? So that's what I'm doing with this. So in other words, I'm just going to say, okay, theta is such that the cosine is positive. And I can do that because, you know, it's my work here. So I'm making that restriction. So what we're going to have is we're going to have 1/4 cosine theta d theta. And on the bottom, notice we have sine squared theta cosine theta. Ah, look at this. That cancels. And now we have this. We have 1/4 1 over sine squared. Wasn't that cosecant? Now we know what the antiderivative of cosecant squared theta is, right? Isn't it negative cotangent? Okay. So look what we have here. We have 1/4, negative 1/4, let's call it, cotangent theta plus c. There's what we have. Now, it's negative because the derivative of cotangent is negative cosecant. So, but we just have a positive cosecant. Now, here's the thing. We don't want to leave it like this because what we've done is we've made our substitutions and we've used the properties of the trig functions to simplify the integral and to get something. But what we need to do now is we need to go back and put everything back in terms of x. We're finished using the trig functions. Now we're going to put them away and see what the x values are. So let's go back to our triangle. And here is theta. Now remember, what we did was we said we made this substitution that x is 4 sine theta. That's what we said. Then that means that sine theta is equal to x over 4. So that's opposite over hypotenuse. And that means that this side right here is 16 minus x squared. Okay, so what we need is cotangent. So cotangent of theta, which is this, is going to be adjacent over, well, it's going to be adjacent over opposite, right? Okay. Okay, so let's see what our answer is here. We got negative 1/4, and this is going to be the square root of 16 minus x squared over x plus c. Everybody see that? So what we're doing is we're looking at specific types of integrals that have these roots in them. And we have 3 types of substitutions that we can make. And the reason we do that is so that we can utilize the properties of the trig functions. And then after we utilize those properties, we put them away and get back in terms of x. We strict the domain of theta enough so that we can take the square root of, a trig function squared. Okay, any questions about that? So now, what it amounts to now is we just practice the different types.